Welcome to SimTPDA Now. This month's topic, SingleSource Stereo and Microstereoscopic 3D. Welcome everybody. Good to see returning participants and maybe a couple of new folks as well. Thank you for taking time out of your busy day. I'm your host, Joel Welch, Director of Professional Development for SimT. Before we get too far along, I would like to thank our sponsors, AJA Video Systems. They have agreed to help support SimTPDA and help to keep it a free member benefit. Today's speaker is a return guest, Mr. Mark Shubin. Mark is a SimT Fellow and a multi-Emmy Award winner. And if you are not aware of his blog at shubincafe.com, a lot of interesting discussion there, and I'll let Mark talk about that when he steps up to the microphone. But Mark, without further delay, the floor is yours.
Thank you, Joel. And just like to tell everybody there's going to be some background noise. Unfortunately, due to some flight cancellations yesterday, I have to give this presentation from a parking bridge at LaGuardia Airport. Let's start off with some of the challenges that 3D TV poses even before we get up to the viewer. The one obvious one is that we seem to need twice as much equipment and signals. Now, in the upper right, I've shown a picture of two cameras. The reason I have a plus after signals is, in addition to the two cameras and two lenses, there's a rig for holding them together. So it's 2 times the information plus. There's also additional personnel. We have to have a convergence operator per pair of cameras, and generally a stereographer for the overall 3D presentation. There's additional processing that's required. One set of processing is for correcting issues that occurred in the pair of cameras, whether one camera has been rotated a little bit or has a different vertical alignment or a horizontal alignment that isn't desired. Another is for matching the video of the two cameras, getting the colors and the grayscale exactly right. And then another range is for formatting the 3D in one of the many ways that 3D is distributed these days. There's an issue with graphics. There's an issue about the z-axis depth. If there's something in the picture that's coming out of the screen and there's graphics in front of it, there will be a conflict between the occlusion cue, the graphics blocking what's coming out, and the stereopsis cue, which is how far in front of the screen the two are, and so graphics are a challenge. Distribution resolution is a challenge at the moment, at least. The HDMI 1.4a standard calls for 1080i pictures to be side by side, which means that the 1920 picture elements that normally would be across the width of an image is actually only 960. And if you're doing 720p images, those are done over-under. And so what should be 720 lines is actually only 360 lines. And then there's some monitoring challenges. I've shown a picture here of a Sony display that uses circular polarization, and notice that there's 2 layers of material in front of the display, a polarizer and a retarder, and because of those layers and the fact that different information is on alternating scanning lines, if you have a vertical angle that is not head-on to the display, you can get ghosting. So those are challenges before we get to the viewer. And then once we get to the viewer, there's another set of challenges. One is that we, at the moment at least, have limited 3D TV penetration. And most of the people who have been shooting 3D will tell you that 3D requires a slower cutting. For one thing, there's time that's required to acquire the 3D image, varies from viewer to viewer. There tend to be smaller lenses used for 3D because people try to get the cameras closer. So at the upper right here, I've shown a rig. It's the Pace Fujinon Shadow rig that was shown at the NAB convention this spring. And what it is, at the bottom is a long lens that would normally be used for 2D coverage of a sports event, and on top of it is 2 cameras and 2 smaller lenses that would be used for 3D coverage of the same event. Then there's glasses. At the moment, most 3D TVs are using active shutter glasses, and those have a significant cost, about $150 per pair at the moment. There are batteries that need to be changed. They need to be maintained. There's compatibility with 2D viewing. At the right in the middle, you can see an image that has a double image on the screen. That would not be acceptable to a viewer who is not wearing glasses, and yet some people are stereo blind or have difficulty with 3D glasses, and if they are joining a family group where the bulk of the people in the family want to watch 3D, then they need some way that they can watch that same display. Some people have proposed using 2D glasses for that, where both eyes get the same image. And then their perceptual conflict, I've shown a sort of roller coaster picture at the lower right. There's a stereovisual vestibular conflict that some people complain about. The sort of thing that causes seasickness is stronger when you have 3D, when your seat is not moving but the image is. That's sometimes called simulator sickness. And then there's a distance-based problem, and I'll talk a little bit more about that in a moment. Okay, here is stereoscopic 3D theory. Sorry, Ray, you're complaining about the bad distortion. Am I talking too loud? I can speak a little lower, but there might be some background noise that you hear. I'll turn myself down a little bit and let me know if that helps. I can also move the mic away a little bit. Okay, here's stereoscopic 3D theory. The theory is that we acquire with 2 cameras that are separated about as much as someone's eyes are, and they're converged on what the viewer's eyes would be converged on, and then in presentation, the viewer looks at the screen, has the exact same angle, and essentially gets exactly what the camera's captured. Well, that's not ordinary stereoscopy. That's called orthostereoscopy. Good. Seeing from Ray that sounds better. Okay, orthostereoscopy is the one particular case where the viewer's eyes happen to match what the cameras are doing. So let's look at what normal 3D has and why orthostereoscopy is very rare and is very unlikely to happen. Here are the other 3 dimensions of 3D. One is pupillary distance. Not everyone has the same pupillary distance, or distance between the centers of the pupils of the eyes, and there's particularly a difference between children and adults. Down to 5-year-olds, you might go down to about 40 millimeter pupillary distance. Adults can go to as much as 80 millimeter pupillary distance. There is a case on record of a 15-year-old girl who had a 43 millimeter pupillary distance. And if you're talking about children who are younger than 5, there can be considerably smaller pupillary distances. Then we have screen size. I'm showing a mobile phone at the left center and a movie theater screen at the right center. The mobile phone image goes down to about 1 inch, and the movie theater screen goes up to about 100 feet. And then finally we have viewing distance. And let's take a sort of orthostereoscopic case. Let's say that we have a negative parallax situation. Negative parallax means that something is going to come out of the screen. And let's say that it happens to match exactly the pupillary distance of the viewer. Well, then it's going to appear to come out of the screen exactly half of the distance that the viewer is from the screen. Well, if the viewer happens to be 100 feet away from the screen, it's going to come out 50 feet. And if the viewer happens to be 6 feet away from the screen, it's going to come out 3 feet. Well, if what's coming out is someone's arm, 3 feet might be sort of okay. If it's 50 feet, that's pretty difficult for someone's arm to be believable. So we have a vast range of vergence space distances for the same 3D master. Vergence space is how your eyes are pointing. That's the vergence of the eyes. There can be convergence when the eyes are pointing towards the center, and divergence when they're pointing apart. So let's see what that looks like. At the lower right of this slide, I've shown the difference between the real world and 3D in terms of vergence and accommodation. Accommodation is the focus of our eyes. Normally in the real world, whatever our eyes are pointing to is whatever our eyes are focusing on. But in 3D, the eyes are always focusing on the screen, wherever the screen happens to be. But the vergence can be at the screen, before the screen, or in front of the screen. You have this great range of vergence. Now, on the left, I've shown the latest diagram from Professor Martin Banks of the Visual Space Perception Laboratory at the University of California in Berkeley. And it shows on the vertical axis accommodation distance, that's how far you are from the screen, and on the horizontal axis, vergence distance, that's what the stereographer is asking you to point at. And the screen is basically that black line that's running diagonally through the image. Now, the dark shaded area, the dark orange area, is called Percival's zone of comfort. That's where people will not get sick if they are having a difference between the accommodation and the vergence distance. The lighter shaded area outside of that is an area where they confuse the two images. They can make one image out of it, but they might get sick when doing so. And then in the white area, they can't even fuse the two images. Well, if you take a movie theater, that'll be up near the top of that diagram. Maybe you're a minimum of 3 meters away from the screen. More likely you're going to be beyond 5 meters from the screen. And essentially you can see anything going out to infinity without getting sick. And it's only information that's so close that it's practically biting you on the nose that will cause you to have discomfort. But if you get down to the lower section of the diagram, that's TV at home. Now you may be watching from a distance of 8 feet or 6 feet or something like that, and now you have a problem not only with things that come way out of the screen, but also with things that go back into the screen out to infinity, and infinity in optical terms is actually fairly close. Infinity and 30 feet are not too different. According to Professor Banks's latest work, he believes that the comfort zone is okay out to infinity if the viewer is sitting at least 3.2 meters away from the screen. That's 10.5 feet. That's sort of at the far end of what someone might be watching a TV set from. Normally TV sets are viewed from a closer distance than that. And he says this is just a guess at this point. More research is needed to say exactly what the zone of comfort is. Here is an illustration from a white paper that was done by In3 showing vergence accommodation conflict in a movie theater. And again, out to infinity is no problem, and this particular diagram says it's okay up to about 8 feet in front of the screen. Here is the same company's indication of what's okay for home theater. And they're saying if you're sitting 6 feet away from the screen, you can only go 4 feet behind the screen and up to 1.8 feet in front of the screen before you start getting some discomfort. Now, there's a way of handling this, which is to reduce the vergence distance. If we simply shoot something for a cinema screen and scale it down to a TV screen, then we eliminate the discomfort problem, but we introduce a new problem, which is miniaturization. If you look at the top right of the image, I've shown a diagram of looking at a corner where the left side of the corner is blue and the right side of the corner is red. Now, the right eye is seeing much more of the right side of the corner and less of the left side of the corner. And the left eye is seeing much more of the left side of the corner and less of the right side of the corner. It's relatively easy to move those left eye and right eye views closer together so that we don't run into a vergence accommodation conflict. But when we do that, we still have the right eye view seeing that much more of the right side and the left eye view seeing that much more of the left side. When that occurs, if we move the left eye and right eye views closer together, we have the sensation that either we're looking at it through the eyes of a giant, and we know that we're not giants, so that sensation goes away right away, or we feel that what we're looking at is much smaller. And many people have complained of 3D that the players on a football field look like chessmen or something like that. Now, I've tried to illustrate this here with a different version of fooling the eye. This looks like maybe a little toy building on a train set. This is actually a full-size building shot in a real photograph, but the blur that was added through tilt-shift photography makes it look like it's miniaturized. And that's the kind of thing that we don't want to have happen on 3D TV. Another problem that we have is ghosting, or crosstalk between the eyes. This picture is an actual image that was shot through a pair of 3D glasses as part of a review of 3D TVs that Gizmodo ran. One was a Panasonic TV, another was a Samsung TV. I'm not going to say which is which here, but you can see on the left side of the head a ghost image. And that can be caused by the glasses, that can be caused by the display, that can be caused by synchronization between the glasses and the display. It can be caused by viewing angle, as I showed with that Sony professional display. It can be caused by the viewer's orientation, if the head is not straight up, or it can be caused by an inability to fuse the images. Here's that spatial resolution that I was telling you about before. Here is a typical 3D transmission through HDMI 1.4a, and you can see that the two images have been squeezed horizontally, so they each have 960 pixels of information instead of the normal 1920. Now, Anaglyph 3D presents some additional challenges. The good part is it's got inexpensive glasses. They're just, say, red and cyan filters, or magenta and green, or blue and some form of yellow or amber. They'll work on any color TV. They'll work with any color TV distribution system, and they deliver full resolution. But they have strong ghosting, and I'll go a little bit more into that in a moment. They have poor color rendition. They can cause eye rivalry, where one eye is getting considerably more light than the other eye. They have potentially significant light loss, and they usually require the viewer to try to do some display adjustment to make things look a little better. Now, here's some research that was done at Curtin University of Technology in Australia on a bunch of Anaglyph glasses. And you can see that the vast majority of them have a terrific stop band, virtually no transmission in the stop band, and pretty good transmission in the pass band. You'll see one pair of glasses doesn't have very good stop band. That one pair of glasses was actually just printed on a computer printer using some colored ink. They just wanted to see what would happen. So that's not something that's commercially sold. All of the commercially sold glasses have very good stop band and pretty good pass band. So you can say, okay, this works really well. Let's not have any ghosting. This works terrifically. But here are the displays that those glasses are used with. So let me back up the slide once more. Notice at around 550 nanometers, there is virtually no transmission on either one of the glasses, and yet here in this next slide for a display shows that the green output is centered on 550 nanometers. And so you're pretty much guaranteed to get ghosting and to have color rendition problems when you use any Anaglyph pair with any existing video display. And this is a broad range of displays in this slide: CRTs, LCDs, DLPs, all sorts of different displays. So we have this elusive grail of 3D. Can there be a 3D system that has no ghosting, no vergence accommodation conflict or miniaturization, 2D viewer compatibility so that anyone can watch the same display even if somebody's watching in 3D and somebody can't watch in 3D, no extra personnel required, just one lens and camera per position, just one signal path and recording per position, full resolution, inexpensive glasses, and works with all TVs and distribution systems. That would be nice, wouldn't it? Well, let's go back in history for a little bit. 3D, as we currently term it, or stereoscopic 3D, sort of started in 1833 with some experiments by the British physicist Charles Wheatstone. He used mirrors. There's two mirrors at an angle in the center of that stereoscope at the top. You kind of stuck your nose up against the mirrors, and your left eye would see the image on the left, and your right eye would see the image on the right. And notice that there's a screw at the bottom so you can adjust the distance. Then in 1849, another British physicist, David Brewster, came up with a lenticular system using lenses for looking at side-by-side images, and that was refined a little bit in the Holmes stereoscope, which is down at the bottom, created by Oliver Wendell Holmes, which had adjustable prismatic lenticular optics. The prisms forced the eyes to look at the side-by-side images. The lenses dealt with any accommodation difference, and then you could move the stereo images back and forth to get the appropriate view. So this took care of all the vergence accommodation conflict without introducing miniaturization. Now, a little bit later than that, in 1881, this happened. A guy by the name of Clement Adet, who was a aviation pioneer, actually, came up with the first stereo sound transmission. And he arranged these microphones along the stage of the Paris Opera and then had a listening room that I'll show you in a moment. But notice that the microphones are fairly well spaced apart. This is a diagram that appeared in Scientific American on December 31st, 1881, and he called his system binauricular audition, but he did compare it to the stereoscope, and so that later became known as stereophonic sound and eventually just stereo. And here is the viewing area. It was a tent, and people held receivers up to each ear, and because they held the receivers up, it was crosstalk-free listening. Now, that form of stereo, today we sometimes call AB stereo or spaced omnidirectional microphones. It gives you a big sensation difference from monophonic sound. You get a sense that you're being enveloped in sound, but it's an unnatural envelopment in sound because the microphones are generally spaced considerably farther apart than our ears are. So they are picking up sounds differently from the way that we would normally hear. And as a result, there is poor mono compatibility. If you try to take sound that was recorded with spaced omnis and presented in mono, you can very easily get phase cancellation at different frequency ranges. So over the years, we have changed our dealing with stereo sound. By the way, this was sort of the beginning of stereo on TV. This was in the late 1950s, early stereo simulcasts, where you would have the TV set in the center, and it would carry a full program of mono sound, and then you were to put your AM radio on the left and your FM radio on the right, and they could do things like ping-pong effects. So something would come out of only the AM radio speaker, and something else would come out of only the FM radio speaker. So there was a huge sensation difference between this and mono. You could say, ooh, I just heard something coming out of the left. Ooh, I just heard something coming out of the right. But it was completely unnatural. Now, we tend to use something called SingleSource Stereo. Some people like to record with an artificial head that has microphones in the ear canals of the artificial head. The diagram that I've shown here, which is from a Shure stereo mic technique tutorial, is called XY technique. There's another technique called MS, or mid-side technique. There are others. They're sometimes called single source, sometimes called coincident microphone. And down at the bottom, I'm just showing a typical stereo microphone for a little handheld recorder. There are also professional versions of stereo microphones, but they tend to be one piece now, and there are many camcorders that have built-in stereo or even surround sound microphones picking up from a single source. That's what we have. And then even in listening, we tend to listen with narrow separation, either single source, like what I've shown at the top. That's a speaker system from a company called Embracing Sound. It's highly regarded. And then down at the bottom, very common Wohler stereo monitoring system that you would find in a rack, and the two speakers are about as close as ears are, maybe a tiny bit farther apart than ears are, but definitely a narrow stereo monitoring, and we decide that this is absolutely fine. Well, does this have any relevance to 3D? Let's look first at visual stereo acuity. I have diagrams here from two different researchers at two different times. Down at the bottom left, there's a diagram that seems to show that you can have stereo acuity, the ability to distinguish that something is in 3D, down to a fraction of 1 arc second, like 3/10 of 1 arc second. There's 60 arc seconds in an arc minute, and there's 60 arc minutes in a degree of arc. So 1 arc second is 1/3600th of a degree of arc, and this 0.3 arc seconds is more like 1/10,000th of a degree of arc. By the way, a pixel for 2020 vision tends to be 1 minute of arc. So we're talking much, much greater sensitivity to stereo acuity than to luminance resolution. And even up at the top, here are two tests with different stimuli, different people involved. You'll notice that a lot of the people, at least on the right chart, are seeing in the range of 9 to 20 arc seconds, the bulk of the people. And even in the top chart, most of the people are seeing within about 60 arc seconds, which would be 1 arc minute. So certainly our stereo acuity is no worse than our luma resolution acuity, and potentially it's considerably better. Now, there have also been many 3D systems that offered limited stereopsis. At the top left, I'm just showing for reference a studio lens from Canon. It's the XJ22 by 7.3 lens. It's not a 3D lens, just a plain old ordinary studio lens. But at the right is Wassel's 3D lens adapter. That's been shown at NAB for about 15 years now. In the center, I have Canon's 3D lens adapter that was shown for the XL1, I think in 2001. At the lower left is the DXG321, which was shown at the Consumer Electronics Show this year. And notice that the two lenses there are probably closer apart than a large thumbnail. And then to the right of that is a new Hammacher Schlemmer 3D camcorder just being sold now, and it has a similar stereo lens separation to the DXG321. And then at the bottom right, I have a Sharp 3D module that would be available for a cell phone or something like that. Now, here's a demonstration that was done by Reality at the Digital Cinema Summit at the NAB show this fall, the SMPTE Digital Cinema Summit, and it was a wonderful demonstration. They were demonstrating problems in 3D pickup when cameras are rotated or there's a vertical disparity or something like that. And notice that line of lights in the hallway overhead. They're high-intensity lights. This wasn't a lit scene, just happened to be a convention center hallway. Well, in many of the demos, I was seeing ghosting in that line of lights because they were very high brightness and they weren't always where the object of interest was. And Steve Schler of Reality asked his operators to try going to a very, very narrow interaxial distance when the axes of the two lenses are brought so close together that it's practically looking at the same thing. And he did this to demonstrate something that is theoretically bad, where there's insufficient interaxial distance. And what I found was this was actually quite good. I found no ghosting. I got a good stereo sensation, and at least from where I was sitting, which was up in the front row and off at an angle to the screen, it was the most comfortable 3D that I had seen during the entire Digital Cinema Summit. So there's something called microstereopsis, which is a term that was coined by Mel Siegel, a senior research scientist at the Robotics Institute at Carnegie Mellon University, and he had some co-authors of two papers, one called Kinder, Gentler Stereo, and one called Just Enough Reality, Comfortable 3D Viewing via Microstereopsis. Both of these were published in Proceedings of the Society of Photographic Instrumentation Engineers in 1999. And they were trying to solve the problem that I mentioned before of simulator sickness. This was not for 3D entertainment. This was if you were in some submarine or something and you had to use a 3D display to see what you were doing, you didn't want to get sick. But the concept is actually much older than 1999, as I'll let you know pretty soon. And the term microstereopsis is not likely to be confused with microstereoscopy, which is a term used for 3D microscopy, although there is a company called Microstereopsis, and they do make 3D microscopy equipment. Now, some researchers at Sony's technology group decided to try this microstereoscopic system, and they built this prototype camera, and you may have seen pictures of this last year. It was shown at the CTEC convention. Notice that it has a standard single lens on the front. That's an ordinary 2/3 inch ENG EFP type lens, but it's a 3D camera. Now, here's what's happening inside the camera. At the left side of the diagram is the standard single lens with its standard iris, and then they have some relay optics, and then at the end of the relay optics, the image is split in two, and the only disparity that you're getting is from the size of the lens elements of the original lens, but it's sufficient that you can get some 3D out of this. And this was shown at the Consumer Electronics Show in 2009, not this year's, but last year's Consumer Electronics Show. Both of those two side-by-side displays there are 3D TVs. The one on the right has the standard double image that you would expect from a 3D TV being viewed without glasses. You put on the glasses, you see 3D. But the one on the left is also showing an image that's 3D. It's also 3D only if you put on the glasses, but without the glasses, the image is actually not too bad. It's something that could be watched. You do not see any double image, and because there is no double image, you cannot have ghosting. Where there is no double image, there cannot be ghosting. So what does the Sony single lens system offer? Well, there's no vergence accommodation conflict whatsoever. Also no miniaturization, because the interaxial distance, the distance between the two lenses, if you will, or in this case the two parts of the one lens, is very much smaller than the distance between our eyes. So we never feel that we have the eyes of a giant and nothing ever gets miniaturized. There is no ghosting. There is full 2D compatibility with the 3D display. If you have a family and three of them want to watch in 3D and one of them wants to watch in 2D, they can all watch the same display at the same time. You only need one lens per camera position, and that can be any kind of lens you want. If you want it to be a very long lens, a 1:1 or something like that, there's no problem. There are no additional personnel required. You don't need a convergence operator because there isn't anything for the convergence operator to do. There's only one lens. But you still do need two cameras per position. You still do need 3D TVs if you want to watch in 3D, and currently that means that you're using the active glasses, which are, as I mentioned before, currently costly. And you do still have that spatial resolution loss in HDMI 1.4a. If you're doing 1080i, you're getting only half of the horizontal resolution, and if you're doing 720p, you're getting only half of the vertical resolution. So, is there something else that we can do? Well, Jimmy D. Songer got a patent in 1973. The reason I mention his name, he's the person who's often credited with inventing video assist for film cameras. And his idea was to put something in the iris plane of a lens. Here's another diagram from his patent, and at the left side you can see the iris plane where the light rays are crossing, and notice that there's something split in two down there, and he has one half of it being blue-green or cyan, and the other half of it being red. So he's putting anaglyph filters into the iris plane of a lens. And then that was improved on in a patent that was issued to Leo Beiser in 1981. And Beiser, I'm mentioning his name because he was one of the inventors of the supermarket laser scanner. And his improvement on the Songer patent was to add a second iris plane in the lens, which would have guillotine blades, so it would be sort of a slit iris, and it would give you separate control over depth of field and light control. And he seems to have sold that patent or been part of a group called Digital Optical Technology Systems that was based in the Netherlands, and this is sort of what their iris looked like. This is the slit iris. The center of the iris, the part that looks white here, is absolutely clear. So anything that is in focus in the picture passes through the center of the iris, completely clear, does not get affected in any way. Anything that's out of focus because it's too far picks up one set of color fringes on the left and another set of color fringes on the right, but only within the defocus zone. There is no double image. It's only the defocus part that gets color fringes. And anything that's out of focus because it's too far picks up the opposite set of color fringes. Now, this was shown in New York in 1979 at an exhibition called New Advances in the Technology of Film, and I was there and I looked at it, and my recollection is that this worked quite well. It was also broadcast by 9TV in Sydney, Australia, which, by the way, you may have seen some press releases recently where they're claiming credit for the first terrestrial 3D television broadcast. They may be right in claiming the credit, but wrong on the date. It wasn't in 2010, it was in 1979 or 1980. So, what about the problem that this is anaglyph? Well, on the left, again, I have the problems of anaglyph, and that's because they have to use saturated filters for crosstalk reduction. So that causes light loss, eye rivalry, poor color, display adjustment, residual ghosting. That's standard anaglyph. But for this system, the filters do not have to be saturated. They can be just barely colored filters because there is no crosstalk. So you do not need the anaglyph to eliminate the crosstalk. You only need the anaglyph to direct the eyes a little bit. So the greenish eye will tend to pick up more of the left view. The magenta-ish eye will tend to pick up more of the right view, and you get your stereopsis that way. So what does microstereoscopic anaglyph provide? As in the Sony system, no vergence, accommodation, conflict, or miniaturization, no ghosting, full 2D compatibility with a 3D display, one lens per camera position, no additional personnel, but it also adds only one camera per position. It works on any color TV and distribution system, don't have to do any side-by-side images, and therefore there's no resolution loss. So this may be an absolutely spectacular system. So why isn't it everywhere? Well, one reason is it was formerly patent protected. I mentioned these two patents, and the ops people certainly had the Beiser patent available to them. They probably had the Songer patent, and so they could prevent anyone from using the system. But those patents have now both expired. They've been expired for several years. Also, unfortunately, perhaps, it doesn't sell new TVs or other new 3D equipment. If this works with all existing TVs, and if you can use standard cameras and pretty much standard lenses, you do have to modify them to put in the extra iris, maybe that's not so good for the people who want to sell new 3D equipment. And also, we are working on my recollection of something that happened 31 years ago, and perhaps it is not as flawless as I've presented it here. But then there's a fourth reason. It offers less wow than other stereoscopic systems, and that's certainly what Steve Sclair was trying to demonstrate at the Digital Cinema Summit when he went to the very limited interaxial distance. It certainly was less 3D-ish, less enveloping than the other stereoscopic systems. But is that necessarily bad? Does microstereopsis bear a similar relationship to common stereoscopy in the same way that single-source stereo sound bore to ping-pong stereo? Is maybe microstereopsis something that's more natural, something that would be better for us to have than a wider interaxial distance? So that's my presentation on microstereopsis, and I think it's something that's worth thinking about. Do we have any questions?
There aren't any in the queue at the moment, but while people do, and let me turn up the audio a little bit here. I'm sorry. I'll move the microphone closer to my mouth. While we wait for folks to queue up their questions, Mark, it doesn't relate specifically to microstereopsis, I don't think, but in preparing for our 3D conference that's going to happen on 13th, 14th of July, a topic has come up, LiDAR. Are you familiar with that technology?
Yeah, it's a way of getting depth information non-optically. So you're using laser ranging in the same way that radar is radio ranging, and you can pick up information about the depth and then apply that to a two-dimensional signal and get depth information that way.
Okay, good. Well, thank you.
Sure.
Let's see. I see Allie has a question.
Yeah, how would the single-lens system provide stereopsis since it looks at a single view? Well, it's microstereopsis. The fact that you have a large lens, some of those light rays, let me go back a little bit to the Sanger patent. Okay, looking at the left side of this slide, you can see that in the iris plane, anything that's perfectly in focus crosses at the iris plane, but anything that's slightly not in the focal plane is going to be a little bit wider in the iris plane, and it's going to pick up a fringe as a result of being slightly to the left or slightly to the right of the center of the lens. So the lens axis is only the very center of the lens, and the width of the lens itself, or the diameter of the lens itself, can be used to give you a tiny bit of 3D separation, and that's something you can take a look at the Sony results. There are other ways of taking a look at microstereopsis. I recommend that you take a look at the papers by Mel Siegel. They're available on the web. Let's see, some other questions here. Dick Perrin says, am I familiar, sorry, somebody just asked something and it went away. Am I familiar with IMV3's process? It's compatible and impressive. I'm not familiar with that, sorry. Willard Buckland says, it's been suggested that the human visual system will evolve rather quickly to overcome the divergence accommodation dissonance. Do I have thoughts on that? Yes, I believe that we possibly can do some training that will help with divergence accommodation. And there's two reasons that I believe this. One is that there has been evolution of perception in the past. When the Lumiere brothers showed their first cinema, the first cinema that anyone paid money for, one of the things that they showed was the arrival of a train at a station. And the train wasn't even coming directly at the camera, so you're looking at a black and white, jerky, possibly dirty image that has no sound whatsoever, and yet some reports from the time said that people were so excited they had to stand up to get out of the way of the train. in the 1920s, Thomas Edison did something called tone tests, where he tried to show that his phonograph was so good that you couldn't tell it from a live opera singer. And so he would have people blindfolded, and he would have an opera singer start singing and then leave the room, and the phonograph would continue. And people said, oh, I can't tell the difference. Well, this is a mechanical needle in a groove phonograph, and people are saying they can't tell the difference between that and a live opera singer. Today we think that's laughable. But it shows that perception can evolve. Now, vergence and accommodation are muscular functions, and when people go skiing for the first time or hiking for the first time, they sometimes get pains that go away as they become more proficient at it. And if we get to a point where there's going to be sufficient 3D, like a whole generation that watches everything in 3D, it may well be the case that they will be able to deal with the vergence accommodation conflict without getting visual fatigue or something like that. There's another reason that I believe that this can happen, and that's when you get a pair of glasses. Anytime you get a pair of glasses, you are tampering with the vergence accommodation cues. And in fact, Percival's zone of comfort was created by an optometrist who was simply working on how people would be able to deal with new glasses prescriptions and how strong they could be without causing people to get sick. We have a question here from Dick Perrin of Atlanta. Do you think dual stream to the home has a chance? I certainly hope so, because it would eliminate a bunch of these resolution issues, but it does mean changing an awful lot of equipment, set-top boxes, that sort of thing. So it's certainly going to take some time. David Trzynski, I hope I pronounced that right. Is this microstereopsis anaglyph in commercial development? Not now. It was in commercial development in the late 1970s, early 1980s by this company that was called Digital Optical Technology Systems, but I am not currently aware of anyone who's developing it. I personally have been talking to some lens manufacturers about them considering putting in the anaglyph iris, because that's the only modification that's required, and at least one major lens manufacturer seems to be interested in doing that. Glenn at Faro says, what was the resolution in the original tests, and how would today's HD or DI formats be impacted, better or worse? I don't know what was done in the original Songer stuff, but he dealt with 65mm film. He worked on The Sound of Music, for example, was one of the movies that he dealt with. So I imagine that he probably used this on extremely high-resolution film. The stuff that I saw was both standard definition, or not even standard definition, but composite color television. But I also saw some print materials. There was an edition of Australian Playboy that was printed using the microstereoscopic anaglyph technique, and it worked very well. John Yeller asks, what codecs are there that exploit the presumably very high correlation between left and right images to achieve high coding gains? There are some. You might want to look at TD Vision. They're one of the ones that's been pushing that. But I think all of the encoder manufacturers are looking forward to something like a 2D plus delta, which is what's being discussed. There was a discussion of 2D plus depth, where you would take, say, the left eye image and you would add depth information, but that's kind of difficult to code. But 2D plus delta is basically what you're talking about, very limited difference between the signals, and therefore that works well in codecs. Jan van Rooij says, isn't there a problem with lateral chromatic aberration of a typical lens? Yes, there probably would be an issue with lateral chromatic aberration, so I guess you have to use a good lens rather than a typical lens. Let's see. Deborah Osborne says, how might a production approach 3D programming made for children and adults with the pupillary distance issues? Well, that's a serious question. You probably have to use the smallest child's pupillary distance as your standard and assume that there's going to be divergence if you do anything more than what the child would see, and then let the adults have the miniaturization that will result from doing that. The microstereopsis technique, or doing any form of technique that goes to a minimum interaxial distance, though, eliminates that problem, because in microstereopsis, the effective interaxial distance is smaller than even the smallest child's pupillary distance. I missed a question. Let me see. It's on here. Yes, sorry. John Maisels from Florida says, if you do a double-blind test, if that's not an oxymoron, how do viewers compare the stereo effect from microstereopsis versus dual lens? Well, I guess it depends on the viewer. There were two people, at least at the Digital Cinema Summit, who had opposite views of that. Steve Sclair of Reality, when he demonstrated the extremely small interaxial distance that was effectively microstereopsis, thought that that was a bad thing and that having dual lens was a good thing. And I, looking at the exact same pictures at the exact same time off the exact same screen, thought that it was the best 3D that I was seeing at the Digital Cinema Summit, and so there's a difference of opinion there. So I'm afraid I can't tell you what everyone will come up with. Double-blind test would be a great idea. I think that we need to have a lot more research on microstereopsis, but there are a fair number of papers out there, and it's worth looking at those at the moment.
And I think that's the end of our questions, Mark.
Okay. Thank you all for participating. And sorry about the background noise. It was unavoidable due to some flying weather.
And I'd like to thank you, Mark. Appreciate you doing it from the airport and using your cell phone. I would like to also thank our sponsor, AJA Video Systems, again, for their generous support.